Let us now come to the second law of thermodynamics. Since the second law of thermodynamics deals with entropy, let us define eta C, which is entropy per unit deformed mass, or eta naught, which is entropy per unit undeformed mass, so that the total entropy carried by the body at any point of time t can be given as rho dV times eta c integrated over omega, or equivalently integrated over omega naught rho naught eta naught d capital V. So this is the total entropy carried by the body. And now remember the heat flux through the surface. The heat flux vector is denoted by Q, and the entropy flux is Q by theta dot N ds for the deformed body, and similarly we can define capital Q by capital theta dot capital N d capital S over the undeformed body. Now theta, small theta, which is a function of small x and t, is the temperature distribution in the deformed body, whereas capital theta, which is a function of capital X and t, is the temperature distribution, equivalent temperature distribution in the undeformed body. So this is the entropy flux in the deformed configuration, and this is the entropy flux in the undeformed configuration. Similarly, R tilde is R by theta, which is the entropy production per unit volume, entropy production rate per unit volume in the deformed configuration. And similarly, R tilde is R by capital theta, entropy production rate per unit volume in the undeformed configuration. So this is the new quantity Q tilde that we defined, which contains the entropy flux and the entropy production rate in the deformed configuration, or equivalently in the undeformed configuration. Now, the second law of thermodynamics states that rate of change of the total entropy minus Q tilde has to be always greater than 0, and we call this difference equal to gamma t, which is the net rate of entropy production. So this contains the entropy flux and the entropy production rate, and this is the rate of change of the entropy carried by the body. So the difference between them is the net rate of entropy production. And if you now write this in the deformed configuration, this ddt of S is rho eta c dV integrated over omega, and Q tilde is the entropy flux and the entropy production rate. So this difference has to be greater than 0, or equivalently we can start with the in the undeformed configuration, we can write a similar statement for the net entropy production rate. Now let us take this and we can start from this as well, but we will first do it with the statement of the second law in the undeformed configuration, and this will lead to a very important inequality called the Clausius-Duhem inequality. We will use this Clausius-Duhem inequality in many ways in the next few lectures. Now let us simplify this a little bit. Let us simplify this term first and convert it into use the divergence theorem to convert it into a volume integral over omega naught. To do that, you realize that this is qk by capital theta. Sorry, this is capital theta and this is capital theta as well. So qk by capital theta nk ds, which is equal to, so this is over del omega naught. Apply the divergence theorem and you get this is del xk, capital Xk of qk by theta dv. This you can take the derivative now over omega naught. So this derivative will give you del qk by del capital Xk 1 by capital theta minus 1 by theta square uh, qk del theta del xk dv over omega naught. So if you write it in vector notation, so this would be over omega naught 1 by theta divergence of q minus 1 by theta square q dot gradient of theta. So that's just this term. So I turn this into a volume integral, which will now contain these two terms, and the rest of the two terms are volume integrals already. So I can now apply the localization theorem and state that now this whole thing has to be greater than equal to 0. This whole thing has to be greater than equal to 0, which means that rho naught eta naught dot has to be greater than equal to this part taken to the right hand side. Now we can remove a few terms from here, especially these two terms. If we go back to the balance of energy that we had derived before, remember the balance of energy was rho naught E0 naught equal to P F dot minus so we can take these two. This is equal to so we use this in the second law. So we have a statement which is kind of a combination of the second law and the first law. So we replace these two terms. These two terms are 1 by theta r minus divergence of q. So we replace this by p f dot minus rho naught e naught. So pf dot minus rho naught, and if we do this, if we replace this r and this, so this is what you will get. And this is the final result, which is the statement of the Clausius-Duhem inequality. So this is the rate of stress work. This is the entropy due to heat conduction, and this whole thing has to be greater than equal to 0. So this is your Clausius-Duhem inequality, which must be satisfied because the second law cannot be violated. So we cannot have a situation where this law is violated. So we cannot have a situation where the left hand side is less than 0. Okay, so um, this is given a name. So this left hand side is given a name. It is given a special name. It's called the internal dissipation, rate of internal dissipation, which is the stress work minus all these terms. And Clausius Duhem inequality says that the rate of internal dissipation always has to be greater than or equal to 0. It always has to be non-negative. For a perfectly reversible process, this will vanish. So a reversible material will not dissipate any energy. So d int will be 0. Also, we know that heat flows from high temperature to low temperature. So the gradient of the temperature will be negative. So Q and the gradient of temperature are going to have opposite signs, so that Q dot gradient of theta is always less than 0. So this whole term is always positive. This whole term is always positive, which means that we can actually have a stronger condition on the rate of dissipation, which says that, so this is always less than, this is always being positive. We can have a stronger condition saying that this part also has to be strictly positive, and that's this statement. This is known as the Clausius-Planck inequality, and the Clausius-Planck inequality is a stronger form of the Clausius-Duhem inequality. We can do this in the deformed configuration as well. So we have to start from here. Again, we do pretty much the same thing. We take this, apply the divergence theorem, and now we will get del xk of qk by theta dv over this, and this will split into 1 by theta del qk del xk minus 1 by theta square del theta del xk qk to dv. So this is how it will split, and then you will apply the Clausius-Duhem inequality again, and then bring in the first law. So the first law in the current configuration, if you remember, the first law in the current configuration was this. So R minus gradient of Q, or gradient of Q minus R, is equal to the stress work rate sigma D minus rho E C dot. So we replace this term in the second law by this. So pretty much like in the reference configuration, this is the expression for the Clausius-Duhem inequality that you get in the deformed configuration. Now, sometimes it is convenient to express this in terms of free energy. In thermodynamics textbooks, free energy is written as internal energy minus Ts. So we are using a different set of symbols here. This we are calling EC, this we are calling theta, this we are calling eta C. So our free energy is EC minus theta eta C. That's the free energy per unit deformed mass. And then I can calculate psi dot. The total derivative of psi dot is total derivative of EC theta dot eta C plus theta eta C dot. So we have EC dot minus theta dot is equal to psi dot plus eta C theta dot, that is equal to EC dot minus theta C dot. So this can be replaced by psi dot plus theta C eta C theta dot. So that's what we have done here, and change the sign. So this becomes less than equal to 0. So we have multiplied it by minus all through. So this becomes less than equal to 0. And for an isothermal process, theta dot is equal to 0. So this vanishes. And this will be the expression for the Clausius-Duhem inequality in the current configuration. In the next lecture, we will see how this can be used to make very important statements about the kind of stress-strain relations or constitutive relations that materials can have.